Alpha Centauri, Latinized from Alpha Centauri, abbreviated Alpha Cen or Alpha Cen, is the closest star system and closest planetary system to the Solar System at 4.37 light-years (1.34%) from the Sun. It is a triple star system, consisting of three stars: Alpha Centauri A, officially Rigil Kentaurus; Alpha Centauri B, officially Toliman; and Alpha Centauri C, officially Proxima Centauri. Alpha Centauri A and B are Sun-like stars, class G and K, and together they form the binary star Alpha Centauri AB. To the naked eye, the two main components appear to be a single star with an apparent magnitude of -0.27, forming the brightest star in the southern constellation of Centaurus and the third brightest in the night sky, outshone only by Sirius and Canopus. Alpha Centauri A has 1.1 times the mass and 1.519 times the luminosity of the Sun, while Alpha Centauri B is smaller and cooler, at 0.907 times the Sun's mass and 0.445 times its luminosity. The pair orbit about a common center with an orbital period of 79.91 years. Their elliptical orbit is eccentric, so that the distance between A and B varies from 35.6 astronomical units or about the distance between Pluto and the Sun, to that between Saturn and the Sun, 11.2 astronomical units. Alpha Centauri C, or Proxima Centauri, is a small and faint red dwarf, class M. Though not visible to the naked eye, Proxima Centauri is the closest star to the Sun at a distance of 4.24 light-years (1.30%), slightly closer than Alpha Centauri AB. Currently, the distance between Proxima Centauri and Alpha Centauri AB is about 13,000 astronomical units (0.21 light-years), equivalent to about 430 times the radius of Neptune's orbit. Proxima Centauri B is an Earth-sized exoplanet in the habitable zone of Proxima Centauri. It was discovered in 2016. Topic: Nomenclature. Alpha Centauri, Latinized to Alpha Centauri, is the system's designation given by Johann Bayer in 1603. It bears the traditional name Rigil Kentaurus, which is a Latinization of the Arabic name Rigil Kentaurus or Rijl al-Kentaurus, meaning the foot of the centaur. The name is frequently abbreviated to Rigil Kent or even Rigil, though the latter name is better known for Beta Orionis. Rigil, an alternative name found in European sources, Toliman, is an approximation of the Arabic Alzaliman as Zalaman in older transcription, at Thalaman, meaning the two male ostriches. An appellation Caswini had applied to Lambda and Mu Sagittarii, also in the southern hemisphere. A third name that has been applied is Bungala, of obscure origin. Allen can only surmise it may have been coined from Beta and Latin ungula hoof. Alpha Centauri C was discovered in 1915 by Robert T. A. Innes, who suggested that it be named Proxima Centaurus, from Latin, meaning the nearest star of Centaurus. The name Proxima Centauri later became more widely used and is now listed by the IAU as the approved proper name. In 2016, the Working Group on Star Names of the International Astronomical Union (IAU), having decided to attribute proper names to individual component stars rather than to multiple systems, approved the name Rigil Kentaurus as being restricted to Alpha Centauri A and the name Proxima Centauri for Alpha Centauri C. On 10 August 2018, the IAU approved the name Toliman for Alpha Centauri B. Topic: Stellar system. Alpha Centauri is a triple star system, with its two main stars, Alpha Centauri A and Alpha Centauri B, being a binary component. The AB designation, or older A times B, denotes the mass center of a main binary system relative to companion stars in a multiple star system. ABC refers to the component of Proxima Centauri in relation to the central binary, being the distance between the center of mass and the outlying companion. Because the distance between Proxima C and either of Alpha Centauri A or B is similar, the AB binary system is sometimes treated as a single gravitational object. Topic: Orbital properties. The A and B components of Alpha Centauri have an orbital period of 79.91 years. Their orbit is moderately eccentric, E equals 0.5179. Their closest approach is 11.2 astronomical units, 1.68 billion kilometers, or about the distance between the Sun and Saturn, and their furthest separation is 35.6 astronomical units, 5.33 billion kilometers, about the distance between the Sun and Pluto. Viewed from Earth, the apparent orbit of A and B means that their separation and position angle (PA) are in continuous change throughout their projected orbit. Observed stellar positions in 2019 are separated by 4.92 arcsec through the PA of 337.1 degrees, increasing to 5.49 arcsec through 345.3 degrees in 2020. The closest recent approach was in February 2016, at 4.0 arcsec through the PA of 300 degrees. The observed maximum separation of these stars is about 22 arcsec, while the minimum distance is 1.7 arcsec. The widest separation occurred during February 1976, and the next will be in January 2056. The most recent, true orbit, closest approach or periastron was in August 1955, and the next will be in May 2035. The furthest orbital separation or apastron last occurred in May 1995, and the next will be in 2075. The apparent distance between Alpha Centauri A and B is rapidly decreasing, at least until 2019. Alpha Centauri C is about 13,000 astronomical units away from Alpha Centauri AB. This is equivalent to 0.21 light-years or 1.9 trillion kilometers. About 5% the distance between Alpha Centauri AB and the Sun. Until 2017, measurements of its small speed and its trajectory were of too little accuracy and duration in years to determine whether it is bound to Alpha Centauri AB or unrelated. Radial velocity measurements made in 2017 were precise enough to show that Proxima Centauri and Alpha Centauri AB are gravitationally bound. The orbital period of Proxima Centauri is approximately 547,000 plus 6,600 minus 4,000 years, with an eccentricity of 0.50 plus or minus 0.08, much more eccentric than Mercury's. Proxima Centauri comes within 4,300 plus 1,100 minus 900 astronomical units of AB at periastron, and its apastron occurs at 13,000 plus 300 minus 100 astronomical units. Topic: Physical properties. Asteroseismic studies, chromospheric activity, and stellar rotation gyrochronology are all consistent with the Alpha Centauri system being similar in age to, or slightly older than, the Sun. Asteroseismic analyses that incorporate tight observational constraints on the stellar parameters for the Alpha Centauri stars have yielded age estimates of 4.85 plus or minus 0.5 gear, 5.0 plus or minus 0.5 gear, 5.2 plus or minus 1.9 gear, 6.4 gear, and 6.52 plus or minus 0.3 gear. Age estimates for the stars based on chromospheric activity, calcium H and K emission, yield 4.4 plus or minus 2.1 gear, whereas gyrochronology yields 5.0 plus or minus 0.3 gear. Stellar evolution theory implies both stars are slightly older than the Sun at 5 to 6 billion years, as derived by their mass and spectral characteristics. From the orbital elements, the total mass of Alpha Centauri AB is about 2.0 m, or twice that of the Sun. The average individual stellar masses are 1.09 m and 0.90 m, respectively, though slightly higher masses have been quoted in recent years, such as 1.14 m and 0.92 m, or totaling 2.06 m. Alpha Centauri A and B have absolute magnitudes of +4.38 and +5.71, respectively. Topic: Alpha Centauri A. Alpha Centauri A, also known as Rigil Kentaurus, is the principal member, or primary, of the binary system. It is a solar-like main sequence star with a similar yellowish color, whose stellar classification is spectral type G2V. It is slightly larger and more luminous than the Sun. Alpha Centauri A is about 10% more massive than the Sun, with a radius about 22% larger. When considered among the individual brightest stars in the sky excluding the Sun, it is the fourth brightest at an apparent magnitude of -0.01, being slightly fainter than Arcturus at an apparent magnitude of -0.04. The type of magnetic activity on Alpha Centauri A is comparable to that of the Sun, showing coronal variability due to star spots, as modulated by the rotation of the star. However, since 2005 the activity level has fallen into a deep minimum that might be similar to the Sun's historical Maunder minimum. Alternatively, it may have a very long stellar activity cycle and is slowly recovering from a minimum phase. Topic: Alpha Centauri B. Alpha Centauri B, also known as Toliman, is the secondary star of the binary system. It is a main sequence star of spectral type K1V, making it more an orange color than Alpha Centauri A. It has around 90% the mass of the Sun and a 14% smaller diameter. Although it has a lower luminosity than A, Alpha Centauri B emits more energy in the X-ray band. Its light curve varies on a short time scale, and there has been at least one observed flare. It is more magnetically active than Alpha Centauri A, showing a cycle of 8.2 plus or minus 0.2 years compared to 11 years for the Sun, and about half the minimum to peak variation in coronal luminosity of the Sun. Alpha Centauri B has an apparent magnitude of plus 1.35, slightly dimmer than Mimosa. Topic: Alpha Centauri C. Alpha Centauri C, better known as Proxima Centauri, is a small main sequence red dwarf of spectral class M6 It has an absolute magnitude of plus 15.60, over 20,000 times fainter than the Sun. Its mass is calculated to be 0.1221 m. Topic: Observation. To the naked eye, Alpha Centauri AB appears to be a single star, the brightest in the southern constellation of Centaurus. Their apparent angular separation varies over about 80 years between 2 and 22 arcsec. The naked eye has a resolution of 60 arcsec, but through much of the orbit, both are easily resolved in binoculars or small telescopes. At -0.27 apparent magnitude combined for A and B magnitudes, Alpha Centauri is fainter only than Sirius and Canopus. It forms the outer star of the pointers or the southern pointers, so called because the line through Beta Centauri Hadar, Agena, some 4.5 degrees west, points to the constellation Crux, the Southern Cross. The pointers easily distinguish the true Southern Cross from the fainter asterism known as the False Cross. South of about 29 degrees south latitude, Alpha Centauri is circumpolar and never sets below the horizon. North of about 29 degrees north latitude, Alpha Centauri never rises. Alpha Centauri lies close to the southern horizon when viewed from the 29 degrees north latitude to the equator, close to Hermosillo, Chihuahua City in Mexico, Galveston, Texas, Ocala, Florida and Lanzarote, the Canary Islands of Spain, but only for a short time around its culmination. The star culminates each year at local midnight on 24 April and at local 9 p.m. on 8 June. As seen from Earth, Proxima Centauri is 2.2 degrees southwest from Alpha Centauri AB, about 4 times the angular diameter of the Moon. Proxima Centauri appears as a deep red star of a typical apparent magnitude of 11.1 in a sparsely populated star field, requiring moderately sized telescopes to be seen. Listed as V645 CEN in the General Catalogue of Variable Stars version 4.2, this UV SETI-type flare star can unexpectedly brighten rapidly by as much as 0.6 magnitudes at visual wavelengths, then fade after only a few minutes. Some amateur and professional astronomers regularly monitor for outbursts using either optical or radio telescopes. In August 2015, the largest recorded flares of the star occurred, with the star becoming 8.3 times brighter than normal on 13 August, in the B-band blue light region. Topic: Observational history. Alpha Centauri is listed in the 2nd century star catalogue of Ptolemy. He gave its ecliptic coordinates, but texts differ as to whether the ecliptic latitude reads 44 degrees 10 south or 41 degrees 10 south. Presently the ecliptic latitude is 43.5 degrees south, but it has decreased by a fraction of a degree since Ptolemy time due to proper motion. In Ptolemy time, Alpha Centauri was visible from Alexandria, Egypt, at 31 degrees north, but, due to precession, its declination is now -60 degrees 51 south, and it can no longer be seen at that latitude. English explorer Robert Hughes brought Alpha Centauri to the attention of European observers in his 1592 work Tractatus de Globis, along with Canopus and Achernar, noting, "Now, therefore, there are but 3 stars of the first magnitude that I could perceive in all those parts which are never seen here in England. The first of these is that bright star in the stern of Argo which they call Canopus. The second, Achernar, is in the end of Eridanus. The third, Alpha Centauri, is in the right foot of the Centaur." The binary nature of Alpha Centauri AB was recognized in December 1689 by Jean Richaud, while observing a passing comet from his station in Puducherry. Alpha Centauri was only the second binary star to be discovered, preceded by a crux. The large proper motion of Alpha Centauri AB was discovered by Manuel John Johnson, observing from St. Helena, who informed Thomas Henderson at the Royal Observatory, Cape of Good Hope of it. The parallax of Alpha Centauri was subsequently determined by Henderson from many exacting positional observations of the AB system between April 1832 and May 1833. He withheld his results, however, because he suspected they were too large to be true, but eventually published them in 1839 after Friedrich Wilhelm Bessel released his own accurately determined parallax for 61 Cygni in 1838. For this reason, Alpha Centauri is sometimes considered as the second star to have its distance measured because Henderson's work was not fully acknowledged at first. The distance of Alpha Centauri from the Earth is now reckoned at 4.396 light-years or 41.59 trillion kilometers. Later, John Herschel made the first micrometrical observations in 1834. Since the early 20th century, measures have been made with photographic plates. By 1926, William Stephen Finson calculated the approximate orbit elements close to those now accepted for this system. All future positions are now sufficiently accurate for visual observers to determine the relative places of the stars from a binary star ephemeris. Others, like Deeporbai 2002, have regularly refined the precision of new published orbital elements. Robert T. A. Innes discovered Proxima Centauri in 1915 by blinking photographic plates taken at different times during a proper motion survey. These showed large proper motion and parallax similar in both size and direction to those of Alpha Centauri AB, suggesting that Proxima Centauri is part of the Alpha Centauri system and slightly closer to Earth than Alpha Centauri AB. Lying 4.24 light-years (1.30%) away, Proxima Centauri is the nearest star to the Sun. Topic: Kinematics. All components of Alpha Centauri display significant proper motion against the background sky. Over centuries, this causes their apparent positions to slowly change. Proper motion was unknown to ancient astronomers. Most assumed that the stars are immortal and permanently fixed on the celestial sphere, as stated in the works of the philosopher Aristotle. In 1718, Edmund Halley found that some stars had significantly moved from their ancient astrometric positions. In the 1830s, Thomas Henderson discovered the true distance to Alpha Centauri by analyzing his many astrometric mural circle observations. He then realized this system also likely had a high proper motion. In this case, the apparent stellar motion was found using Nicolas Louis de Lacai's astrometric observations of 1751 to 1752, by the observed differences between the two measured positions in different epochs. Calculated proper motion of the center of mass for Alpha Centauri AB is about 3,620 mas milli-arcseconds per year toward the west and 694 mas y toward the north, giving an overall motion of 3,686 mas y in a direction 11 degrees north of west. The motion of the center of mass is about 6.1 arcmin each century, or 1.02 degrees each millennium. The velocity in the western direction is 23.0 km per second and in the northerly direction 4.4 km per second. Using spectroscopy, the mean radial velocity has been determined to be around 22.4 km per second towards the Solar System. Since Alpha Centauri AB is almost exactly in the plane of the Milky Way as viewed from Earth, there are many stars behind them. In early May 2028, Alpha Centauri A will pass between us and a distant red star, when there will be a 45% probability that an Einstein ring will be observed. Other conjunctions will also occur in the coming decades, allowing accurate measurement of proper motions and possibly giving information on planets. Topic: Predicted future changes. As the stars of Alpha Centauri move closer to the Solar System, their measured proper motions, trigonometric parallaxes and radial velocities slowly increase. These effects will continue until the star system reaches its nearest point to the Sun, and then reverse as the distance increases again. Furthermore, other small changes also occur with the binary star's orbital elements. For example, in the apparent size of the semi-major axis of the orbital ellipse will increase by 0.03 arcsec per century. Also, the observed position angles of the stars are also subject to small cumulative changes, additional to position angle changes caused by the precession of the equinoxes, as first determined by W. H. van den Bos in 1926. Based on the system's common known proper motion and radial velocities, Alpha Centauri will continue to change its position in the sky significantly and will gradually brighten. For example, in about 6200 AD, Alpha Centauri's true motion will cause an extremely rare first-magnitude stellar conjunction with Beta Centauri, forming a brilliant optical double star in the southern sky. It will then pass just north of the Southern Cross or Crux, before moving northwest and up towards the present celestial equator and away from the galactic plane. By about 29,700 AD, in the present-day constellation of Hydra, Alpha Centauri will be 1.00% or 3.3 light-years away, though later calculations suggest 0.90% or 2.9 light-years in 29,000 AD. At nearest approach, Alpha Centauri will attain a maximum apparent magnitude of -0.86, comparable to present-day magnitude of Canopus, but it will still not surpass that of Sirius, which will brighten incrementally over the next 60,000 years, and will continue to be the brightest star as seen from Earth other than the Sun for the next 210,000 years. About 28,000 years from now, the Alpha Centauri system will begin to slowly move away from the Solar System, and this bright yellow star will eventually fall below naked eye visibility. Topic: Planetary system. Topic: Confirmed planets. Only one planet has been confirmed for the Alpha Centauri system, Proxima Centauri B. It is slightly larger than the Earth, and orbits around Proxima Centauri in its habitable zone. The existence of Proxima Centauri B was announced in 2016 by the European Southern Observatory. It was found using the radial velocity method, where periodic Doppler shifts of spectral lines of the host star suggest an orbiting object. Topic: Controversial and hypothetical planets. Topic: Alpha Centauri B flat. In 2012, a planet around Alpha Centauri B was announced, Alpha Centauri B flat, but in 2015 a new analysis concluded that it almost certainly does not exist and was just a spurious artifact of the data analysis. Topic: Unconfirmed discovery. Whilst ruling out the existence of Alpha Centauri B flat, a possible transit of a separate exoplanet in 2013 was observed. The transit event could correspond to a planetary body with a radius around 0.92 r. This planet would most likely orbit Alpha Centauri B with an orbital period of 20.4 days or less, with only a 5% chance of it having a longer orbit. The median of the likely orbits is 12.4 days with an impact parameter of around 0 to 0.3. Its orbit would likely have an eccentricity of 0.24 or less. Like the probably spurious Alpha Centauri B flat, it likely has lakes of molten lava and would be far too close to Alpha Centauri B to harbor life. Topic: Hypothetical planets. Additional planets may exist in the Alpha Centauri system, either orbiting Alpha Centauri A or Alpha Centauri B individually, or in large orbits around Alpha Centauri AB. Because both stars are fairly similar to the Sun, for example, in age and metallicity, astronomers have been especially interested in making detailed searches for planets in the Alpha Centauri system. Several established planet hunting teams have used various radial velocity or star transit methods in their searches around these two bright stars. All the observational studies have so far failed to find evidence for brown dwarfs or gas giants. In 2009, computer simulations showed that a planet might have been able to form near the inner edge of Alpha Centauri B's habitable zone, which extends from 0.5 to 0.9 astronomical units from the star. Certain special assumptions, such as considering that the Alpha Centauri pair may have initially formed with a wider separation and later moved closer to each other, as might be possible if they formed in a dense star cluster, would permit an accretion-friendly environment farther from the star. Bodies around Alpha Centauri A would be able to orbit at slightly farther distances due to its stronger gravity. In addition, the lack of any brown dwarfs or gas giants in close orbits around Alpha Centauri make the likelihood of terrestrial planets greater than otherwise. A theoretical study indicates that a radial velocity analysis might detect a hypothetical planet of 1.8 m in Alpha Centauri B's habitable zone. Radial velocity measurements of Alpha Centauri B with high-accuracy radial velocity planet searcher spectrograph ruled out planets of more than 4 m to the distance of the habitable zone of the star orbital period p equals 200 days. Current estimates place the probability of finding an Earth-like planet around Alpha Centauri at roughly 85%. The observational thresholds for planet detection in the habitable zones by the radial velocity method are currently 2017 estimated to be about 50 m for Alpha Centauri A, 8 m for Alpha Centauri B, and 0.5 m for Proxima Centauri. Early computer-generated models of planetary formation predicted the existence of terrestrial planets around both Alpha Centauri A and B, but most recent numerical investigations have shown that the gravitational pull of the companion star renders the accretion of planets difficult. Despite these difficulties, given the similarities to the Sun in spectral types, star type, age and probable stability of the orbits, it has been suggested that this stellar system could hold one of the best possibilities for harboring extraterrestrial life on a potential planet. In the Solar System, Jupiter and Saturn were probably crucial in perturbing comets into the inner Solar System, providing the inner planets with a source of water and various other ices. In the Alpha Centauri system, Proxima Centauri may have influenced the planetary disk as the Alpha Centauri system was forming, enriching the area around Alpha Centauri with volatile materials. This would be discounted if, for example, Alpha Centauri B happened to have gas giants orbiting Alpha Centauri A or vice versa, or if Alpha Centauri A and B themselves were able to perturb comets into each other's inner system as Jupiter and Saturn presumably have done in the Solar System. Such icy bodies probably also reside in Oort clouds of other planetary systems. When they are influenced gravitationally by either the gas giants or disruptions by passing nearby stars, many of these icy bodies then travel starwards. Such ideas also apply to the close approach of Alpha Centauri or other stars to the Solar System, when, in the distant future, the Oort cloud might be disrupted enough to increase the number of active comets. To be in the habitable zone, a planet around Alpha Centauri A would have an orbital radius of about 1.25 astronomical units so as to have similar planetary temperatures and conditions for liquid water to exist. For the slightly less luminous and cooler Alpha Centauri B, the habitable zone is closer at about 0.7 astronomical units, 100 million kilometers, with the goal of finding evidence of such planets. Both Proxima Centauri and Alpha Centauri AB were among the listed Tier 1 target stars for NASA's Space Interferometry mission (SIM). Detecting planets as small as 3 Earth masses or smaller within 2 astronomical units of a Tier 1 target would have been possible with this new instrument. The SIM mission, however, was cancelled due to financial issues in 2010. Topic: Circumstellar disks. Based on observations between 2007 and 2012, a study found a slight excess of emissions in the 24 micrometers mid-far infrared band surrounding Alpha Centauri AB, which may be interpreted as evidence for a sparse circumstellar disk or dense interplanetary dust. The total mass was estimated to be between 10⁻⁷ to 10⁻⁶ the mass of the Moon, or 10 to 100 times the mass of the Solar System's zodiacal cloud. If such a disk existed around both stars, Alpha Centauri A's disk would likely be stable to 2.8 astronomical units, and Alpha Centauri B's would likely be stable to 2.5 astronomical units. This would put A's disk entirely within the frost line, and a small part of B's outer disk just outside. Topic: View from this system. Equals. The sky from Alpha Centauri AB would appear much as it does from the Earth, except that Centaurus would be missing its brightest star. The Sun would appear as a yellow star of apparent magnitude plus 0.5, roughly the same as the average brightness of Betelgeuse from Earth. It would be at the antipodal point of Alpha Centauri AB's current right ascension and declination at 02h 39 meters 35 plus 60 degrees 50 2000 in eastern Cassiopeia, easily outshining all the rest of the stars in the constellation. With the placement of the Sun east of the magnitude 3.4 star Epsilon Cassiopeiae, nearly in front of the Heart Nebula, the W line of stars of Cassiopeia would have a W shape. The winter triangle would not look equilateral, but very thin and long, with Procyon outshining Pollux in the middle of Gemini, and Sirius lying less than a degree from Betelgeuse in Orion. With a magnitude of -1.2, Sirius would be a little fainter than from Earth but still the brightest star in the night sky. Both Vega and Altair would be shifted northwestward relative to Deneb, giving the summer triangle a more equilateral appearance. Alpha Centauri is inside the G cloud, and its nearest known system is the binary brown dwarf system Lumen 16 at 3.6 light-years, 1.1%. Topic: Other names. In modern literature, Rigil Kent, also Rigil Kent and variants, and Toliman, are used as colloquial alternative names of Alpha Centauri, then became the proper name of Alpha Centauri B in 10 August 2018 by approval of IAU. Rigil Kent is short for Rigil Kentaurus, which is sometimes further abbreviated to Rigil or Rigil, though that is ambiguous with Beta Orionis, which is also called Rigil. The name Toliman originates with Jacobus Golius's 1669 edition of Al-Farghani's compendium. Toliman is Golius's Latinization of the Arabic name Alzulman al-Zulman, the ostriches, the name of an asterism of which Alpha Centauri formed the main star. During the 19th century, the northern amateur popularist Elijah H. Burritt used the now obscure name Bungala, possibly coined from beta and the Latin ungula, hoof. Together, Alpha and Beta Centauri form the Southern Pointers, or the Pointers, as they point towards the Southern Cross. The asterism of the constellation of Crux, in Chinese astronomy, Nanmen Nanmen, meaning Southern Gate, refers to an asterism consisting of Alpha Centauri and Epsilon Centauri. Consequently, the Chinese name for Alpha Centauri itself is Nanmen the second star of the Southern Gate. To the Australian Aboriginal Boorong people of northwestern Victoria, Alpha Centauri and Beta Centauri are Bermbermgal, two brothers noted for their courage and destructiveness, who speared and killed Chingal, the emu, the Coalsack Nebula. The form in Watjabaluk is Bram Bram Bolt. Topic: Future exploration. Alpha Centauri is a likely first target for manned or unmanned interstellar exploration. Using current spacecraft technologies, crossing the distance between the Sun and Alpha Centauri would take several millennia, though the possibility of nuclear pulse propulsion or laser light sail technology, as considered in the Breakthrough Starshot program, could reduce the journey time to decades. An objective of such a mission would be to make a flyby of, and possibly photograph, planets that might exist in the system. The existence of Proxima Centauri B, announced by the European Southern Observatory (ESO) in August 2016, would be a target for the Starshot program. In January 2017, Breakthrough Initiatives and the ESO entered a collaboration to search for habitable planets in the Alpha Centauri system. The agreement involves breakthrough initiatives providing funding for an upgrade to the VISIR (VLT) imager and spectrometer for mid-infrared instrument on ESO's Very Large Telescope (VLT) in Chile. This upgrade will greatly increase the likelihood of planet detection in the system. Topic: Distance estimates. Topic: See also Alpha Centauri in fiction. List of nearest stars and brown dwarfs. Project Longshot. Sagan Planet Walk. Notes